Alright, so in this video we're finally going to apply the Laplace transform to solving a second order differential equation. In this case we have a non-homogeneous one with a constant coefficient of 1, and we're given the following initial conditions. So from the last video we saw that applying the Laplace transform to a second derivative gives us the following expression, and in this case we're gonna just put the initial conditions in here. So this is going to be k, and this right here is just going to be 0, so we're gonna forget about that term. Laplace transform of the function of time is going to be equal to the function of frequency, and from the tables that I have included in a link in the description, we can find that Laplace transform of a constant 1 is equal to 1 over s. So what we're gonna do is we're gonna put all of this back into the original differential equation, and we're gonna replace everything by a function of frequency. So we're gonna end up with this one here. And now by some algebraic manipulation, we're just going to separate this so that we have y as a function of frequency alone, and then some manipulation leads to the following equation. So basically what I did here is I had the s squared minus 1 that factored because the y factor out of that, and we know that s squared minus 1 can be written as s plus 1 s minus 1. So because we're going to use partial fractions now to separate those terms in the denominator, it is usually easier to start with first order terms. So we want to simplify as much as we can in the denominator before moving on. And now I'm just going to call this function p, and I'm going to call this function q. So the idea now with partial fractions is that, so let's start with p. We're going to have s minus 1, s plus 1 equals to some constant a over s plus some constant b over s plus 1 plus some constant c over s minus 1. Now we multiply both sides by this denominator, so we're going to get a s minus 1 s plus 1 plus bs s minus 1 plus c s plus 1. So now the next step from previous videos that we have done on the partial fractions method, basically what we want to do is we want to choose values of s that will basically make the constant 0. So if we put 0 here, for example, then this constant is going to vanish and this one is going to vanish as well, and we're going to be left with a. So if we put 0 here and 0 there, then we're left with a times minus 1 times 1, so that's going to be minus a. And then as a solution we're going to have a equals to minus 1. Then we can do the same, we can replace s by positive 1, that would get rid of the a and of the b, and we would be able to solve for the c, so c would be 1 over 2. And then we do the same for s plus 1, so s, which is s equals to minus 1, and that would get rid of both a and c, and then we can solve for b. So in the end, I'm just going to write this down because it's pretty routine. I'm not going to go through the whole process here. We should it's a very standard partial fractions derivation. So in the end what you should end up with is the following. So your function p should be equal to minus 1 over s plus 1 over 2 times 1 over s plus 1 plus 1 over 2 times 1 over s minus 1. And then for qs you apply the same method, but now you're going to have what we had before, which is this s at the top. So obviously that's going to create two new constants that you need to solve for using partial fractions. And what you're going to get from the decomposition is the following function. So you're going to get k over 2 times 1 over s plus 1 plus k over 2 times 1 over s minus 1. Now obviously our y of s, which is what we're going to solve for, is going to be p plus q. So if we put these terms together, basically what we get is k minus 1, sorry, k plus 1 over 2 times 1 over s plus 1 plus k plus 1 over 2 times 1 over s minus 1, and all of that. So I'm just gonna make some room here. Gonna get rid of this. Final term is gonna be minus 1 over s. So what do we want to do now? Well, obviously we want our solution in terms of time. So in order to get from here to the function of time, we're going to apply the inverse Laplace transform to each of these functions here, because the Laplace transform has the property of linearity. If we have AF plus BG, where A is a constant and B is a constant, and F and G are functions of time, then that's equal to the Laplace transform of, so A Laplace transform of F plus the B Laplace transform of G. And that's quite messy, so I'm just gonna get rid of that. But you get the general idea behind it. So that's what we're gonna apply to this equation. So for the first term, we're gonna have k plus 1 over 2. Now this is just a constant, so the Laplace transform is only going to be acting on this. So from the tables, we can find that the inverse Laplace transform of this is going to be e to the power of minus t. Then for this one, it's going to be k plus 1 over 2 times e to the power of plus t. And then finally, for this one, we're just going to get minus 1. And that's going to be our general solution, our particular solution, because this is including the initial conditions that we were given in the problem. So you can actually try to solve these same differential equations using undetermined coefficients, and you will get the same solution. Now obviously you might be wondering, well, it seems like undetermined coefficients would be a faster method in this case. Like in here we had to use all these steps, we had to use partial fractions, then we had to invert the Laplace transform and so on. So it seems like quite a tedious process, but the idea is the Laplace transform can actually work for a whole range of differential equations. So it could work for something like this, where you have a function in front of a derivative equals to another function of t. So that's the power of the Laplace transform. It actually can solve functions like this, whereas undetermined coefficients only works when you have constant terms in front of all the y terms and its derivatives. So this is just a simple example to illustrate how it is used and how it can be implemented to solving differential equations. Now, in the next video, I'm just going to go through some more examples on solving differential equations, and after that, we're going to move into partial differential equations.